Hello and welcome again to my physics online video lecture series. Today's video we're going to be talking about the Michelson Morley experiment. This experiment is often sort of cited as one of the important experiments that confirms the theory of special relativity. Oddly enough, that is not what the experiment historically was attempting to do. In fact, the experiment precedes the theory of special relativity by more than a decade and a half. What they actually were interested in doing was attempting to measure the relative velocity between the Earth and the luminous ether, or the luminiferous ether. So the idea behind this experiment, you might recall, is that they wanted to measure how fast is the so-called ether wind. Now, there were a bunch of other experiments and theories that kind of occurred leading up to this experiment. And then there were actually subsequent experiments after this, basically to establish whether or not there was motion relative between the Earth and the ether. So the idea was that Maxwell's equations predict the speed of light, and the speed of light was assumed to be relative to some medium called the ether, which carried light. And a variety of experiments and theories and observations and everything had been made to try to figure out, okay, is the ether dragged along by the Earth? Is it partially dragged by the Earth? Is it stationary and the Earth is moving through it? These experiments are not usually discussed, I think, to the detriment of the completeness of the rest of this discussion. They're not really discussed in most introductory or even modern physics textbooks. But quite a few physicists of the 19th century, including Fizeau, Stokes, Fresnel, Lorentz, all worked on either the theory or the experiment or both related to the ether. All of this predated Michelson and Morley's experiments, by the way. There were kind of three broad theories about the ether. Again, all the theories agreed that the ether was some medium that light could move through. That it may not be otherwise a material, that they didn't expect it to be something like air or something like that in outer space. They just expected there to be some sort of medium that light passed through. And the basic theories behind this include that the ether is totally stationary, that the ether is partially dragged, or that the ether is totally dragged by the Earth. So ether being partially dragged by the Earth is championed by, among others, Augustin Jean Fresnel. The ether being totally dragged by the Earth, at least locally, was championed by, among others, George Stokes. I'm not really sure who the people were that suggested that it's not dragged at all. It may be kind of like the default theory was no dragging at all. But it's worth noting that these top two both predict an ether wind of some sort, and then the bottom one would predict no ether wind. So if the ether on or near the Earth is moving at the same velocity as the Earth, then there's no sort of effective ether wind, if you will, from it. And that means that any experiment done to measure the speed of light will not detect any changes due to the fact that the Earth is moving. And so in some sense, what the Michelson Morley experiment is actually doing is distinguishing between these two sets of, namely, is the ether wind being dragged entirely by the Earth? Is the ether being dragged entirely by the Earth such that there's no so-called ether wind, or therefore change in measured speed of light if you are moving with the Earth? If you are sort of measuring in the direction that the Earth is moving versus measuring against the direction the Earth is moving? Or is there some partial drag, in which case you expect there to be a change in the speed of light? And it should be noted that up till this point in time that Michelson and Morley attempted their experiment, there hadn't been any good way of measuring the effects of the sort of speed of the Earth on light speed, because the Earth's motion about the sun and even the Earth and Sun's motion about the galaxy are both very slow compared to light. So a high precision experiment was needed. So again, Fizeau, in addition to doing some direct experiments on trying to measure ether drag, actually did a successful terrestrial measurement of the speed of light at all. But his experiment had maybe like a 5% error. It differed from the sort of accepted result, the now accepted result, by about 5%. But the uncertainty in his experiment was also on the order of 5%, and it was a known uncertainty. So we needed something, even if we included the idea of the Earth moving about the galaxy, which was not something that we really knew very well at that point in time. We certainly didn't have a good estimate of the speed of the Earth and Sun moving about the galactic core. But even if we did account for that motion, we're still looking at something like 1/100th of 1% of the speed of light. And so that's quite small compared to the level of imprecision that we had in making measurements of the speed of light. So the Michelson-Morley experiment makes use of a Michelson interferometer. It's not the first use of the Michelson interferometer. Michelson actually invented the interferometer and did the Michelson experiment itself. So Michelson's original experiment was in 1881, and what he basically did was build a Michelson interferometer. So light enters into a beam splitter. Let's put the beam splitter like this. Beam splitter will just represent like this. It goes in two parallel paths. Then it basically hits a pair of mirrors. So mirror 1 and mirror 2. And then reflects back off of those mirrors like so. And then recombines in the beam splitter. There's actually some going this way, some coming back this way. And essentially what he expected from this original experiment is, if let's say that the Earth happens to be moving in this direction, so let's say Earth moves this way as it's moving about the sun. So what he expected was that because the light traveling to mirror 1 is moving perpendicular to the Earth, it's basically not experiencing an ether wind. That was the idea, if the ether is being dragged, if there is an ether wind. So this light, there would be no ether wind. And then up here, we expect for this one, ether wind. The expectation of this experiment was that if Earth is moving through an ether, then light traveling to mirror 1, which experiences no ether wind, would take less time than light traveling to mirror 2, which would experience both a headwind and a tailwind going sort of towards and away from respectively. That it would move faster towards mirror 2, slower towards mirror 2, because it'd be experiencing sort of headwind, and then it'd be moving faster coming away from mirror 2. But that the amount of time lost in the slower is more than the time gained in the faster return trip, so it would take a little bit longer to travel to and from mirror 2 than from and to mirror 1. What he therefore expected is to essentially measure a fringe shift, actually not a very big one, like 0.04 fringes was what he calculated. He measured like 0.02 fringes, and a later set, I think Lorentz and Potier essentially said, you've made an error in calculation and you should be measuring 0.02 fringes if there's no ether wind. And so his measurement was kind of consistent with that. The problem was that the error in his measurement was also large enough that he couldn't really make a conclusion. So the error was too large to conclude, is there a wind or not? So basically, this is what set the stage for the Michelson Morley experiment. Basically, they wanted to conduct this experiment with better precision, less measurement error, to see is there an ether wind or not. So this one again uses a Michelson interferometer. So it's the same basic interferometer as in the original Michelson experiment, but with this added twist. Instead of being a stationary interferometer, the interferometer would rotate. The reasoning behind this Michelson Morley experimental setup, as opposed to the initial Michelson experiment, is that there's an assumption kind of built into the Michelson original 1881 experiment, which is that the Earth is moving in a known direction, meaning you can set up mirror 2 to be in the direction that the Earth is moving, and mirror 1 perpendicular to that. And as I mentioned in discussing this experiment, it was kind of just assumed that the Earth is going around the Sun, and they didn't necessarily know much about, is the Sun going around the galactic core, is the Milky Way galaxy itself moving, all of that. So this assumption that the Earth is moving in this direction may or may not have been a valid assumption. And even if we factor in things like, is the Earth moving through the galactic core, etc., may or may not be a valid assumption. So the Michelson Morley experiment, the big modification that it has made is by allowing the entire experiment to rotate. Basically, they eliminate any uncertainty that might be caused by, say, what if the Earth happened to have been moving in some other direction. So if the Earth was moving, say, in this direction rather than the assumed direction of motion, then both of these two mirrors would experience equal amounts of headwind, and so there should be no fringe shift. But if the Earth is actually moving in this direction, and you start here and you rotate through a full 90 degrees, or better yet, you keep rotating and go through several full revolutions, then you actually expect to again see some fringe shifts. And if the rest of the calculation was correct for Michelson and Morley, maybe those fringe shifts would be on the order of 0.2 or 0.02 fringe shifts difference between what is shown in yellow here and what's shown in yellow here. And by going through full rotations, both of these yellows might actually come to pass, even if initially you happen to be pointing along an orientation like the green. In other words, the actual direction in which the Earth is moving becomes irrelevant. Only the relative speed between the Earth and the ether should matter. So this basically corrects the error in the original Michelson-Morley experiment, in the original Michelson experiment, by allowing the entire interferometer to rotate. And so to that end, basically what they did was they set up the Michelson interferometer, but on a large sandstone slab that then floated on a pool of mercury and could basically be given a slight push and basically rotate with minimal friction so that the arms have basically spun about. So once this interferometer is given a push, which causes it to rotate, so kind of a torque push like this, the experiment would involve just watching the fringes and seeing how much of a fringe shift do we observe. And if the Earth is moving very fast relative to the ether and relative to the speed of light, if it's moving at something approaching the speed of light relative to the ether, let's say, then we would expect to see large fringe shifts. If it's moving very slowly compared to the ether, in other words, if the ether is being dragged along, or if the Earth is stationary relative to the ether, then we expect there to not be any fringe shifts as this slab is rotating. So that's the basic experiment. And because this video has run fairly long, I'm going to kind of call this part 1, where part 2 will now be to discuss the actual math behind the experiment, what were the expected fringe shifts, and what did they observe. So in some sense, what I've done here is sort of set the stage for the experiment and its results, but I haven't explained to you what the stage is, what the results are, what happened in the experiment. So hopefully you've enjoyed this, and look for part 2. And as always, thanks for watching.